Hello. Today we will be exploring the world of quantum mechanics by doing a famous experiment from the year 1801. This is Thomas Young's Double-Slit Experiment. Since the days of Newton, scientists have believed that light consists of particles and travels like a beam of particles. Young's double-slit experiment showed that light also travels in waves, just like sound waves or waves in water. Firstly, you need a piece of dark cardboard with two narrow slits cut into them, about 1 millimeter or less apart. We shine the focused light through the slit. In this case, we'll be using a laser. You would perhaps expect the light to produce two spots of light or two lines as it passes through the two slits and hits the screen on the other side. Let's see what actually happens. You can see that the laser does not just produce two lines, but produces a long series of many lines. This is because the light comes out as two waves of light and not as two parallel beams of light particles. The lines of the two waves then bump into each other, producing what is called the interference pattern that we see on the screen. Let's repeat the experiment with two slides that have been accurately printed slits in them. The first has slits that are 0.5 millimeters exactly apart, and the second has slits that are 0.1 millimeter apart. We will then measure the distance between each of the interference lines. Let's start with the slits that are 0.5 millimeters apart. This is the interference pattern produced by the slits that are 0.5 millimeters apart. You can see that the interference lines are further apart than the previous pattern produced by the slits on the cardboard. We will measure the distance between the dark lines. The distance is approximately 7.5 millimeters. We will now continue the experiment with the slits that are 0.1 millimeter apart. This is the interference pattern produced by the slits that are 0.1 millimeter apart. You can see that the interference lines are much further apart than the previous pattern produced by the slits that were 0.5 millimeters apart. We will measure the distance between the dark lines. They are around 35 millimeters apart. We can use the following equation to calculate the wavelength of light in Young's experiment. Delta x is the distance between adjacent dark lines. L is the distance between two sources of light from the screen. Lambda is the wavelength of light, and d is the distance between two sources of light. We measured the distance between the laser and the screen, which was 6.75 meters. We knew that the distance between the two slits, that is 0.5 millimeter and 0.1 millimeter, and we measured the distance between the interference lines that we created, that is 7.5 millimeters and 35 millimeters. Using the measurements we made during our experiments, we can now use Young's equation to calculate the wavelength from the light from the laser. This should be between 560 nanometers and 520 nanometers. If we look at the laser itself, you can see that our calculations for the wavelength of the light are quite close to the laser's wavelength specification, that is 530 nanometers. Yes. Young's experiment showed that although a light beam consists of particles, it also behaves as a wave. Light is neither wave or particle, it is actually both. This is called the wave-particle duality, and this is a concept started the weird and wonderful science of quantum mechanics. And quantum mechanics is really weird. For example, later experiments showed that it's not only light that has wave-particle duality, even matter behaves both as particles and waves. That includes laser pens, computers, even you and me. But that's perhaps for a later video. Until then, thank you for watching.